We have a new state-of-the-art benchmark on OSWorld for artificial intelligence agents performing real-world tasks on digital devices and systems, including macOS, Windows, and Ubuntu. Examples of those tasks are shown here. There are 369 real-world tasks in all, involving interactions with systems and software ranging from Google Chrome and Microsoft Office to Thunderbird and a Python library that can click on buttons or input text. Measured against this benchmark, it's pretty easy to see that we have a long way to go. The humans we tested could accomplish over 72% of the tasks in the benchmark, but the best model on the leaderboard today can do only 22% of those. And with that as context, we turn now to a very recent paper where the authors present an approach for creating a personal assistant by deploying many specialized agents. For the test, 20 specialized agents were made available, and testing was done on all 369 of the tasks from OSWorld for desktop, and also on the 45 tasks from APPAgent, which is a similar benchmark for mobile applications. The result was a new state-of-the-art performance on those benchmarks, as we will see. For context, an AI agent is an autonomous entity that perceives its environment, makes decisions, and acts on those decisions to achieve specific goals based on its programming or learned behavior. The key elements of this definition are 1. Interaction with the environment, which can be physical, like a robot in a fulfillment center, or virtual, like a chatbot responding to messages. 2. The ability to perceive, as when a self-driving car uses cameras and LiDAR, for example, or when a virtual assistant interprets text that it must respond to in some way. 3. Decision-making, for example, when reinforcement learning is used to guide the actions an agent takes in order to maximize cumulative rewards over time. And goal-oriented behavior, such as minimizing errors or maximizing efficiency. And out of the many applications where agents can be used, the focus of this research was specifically agents that are acting as a personal assistant on a digital device, like a laptop or cell phone. The key idea behind the approach we're about to review is that the diversity of requests made in real-world settings is very great. So, therefore, a diverse workforce of lightweight, specialized agents might be more likely to achieve best-in-class results as compared to even a gigantic but monolithic model. And those lightweight agents would surely accomplish their goals with a much lower investment in computing resources, provided that there's an effective way to select and deploy those agents and to scale the number of agents over time. That's the idea. So, here's an example of one of those tasks that's part of OSWorld. It reads like this. In a new sheet with 4 headers, year, CA changes, FA changes, and OA changes, calculate the annual changes for the current assets, fixed assets, and other assets columns. Okay, so this is an example of a request that requires understanding of how to work within a specific application, Excel in this case. The agent needs to access the file, launch Excel, which it will do using a command line interface, create a new spreadsheet, add the new headers as specified, and populate a new table with the year-on-year changes for current assets, fixed assets, and other assets. And that's a pretty good example of where a generalized model might not succeed because it simply lacks the training or tools that would be needed in order to perform this particular series of steps in Excel. And here's one more example. It says, find the daily paper and take down the meta information of papers on March 1, 2024 in the opened PPTX file. Please conform the format and complete others. A rather poorly worded request, by the way, which is part of the test, actually. So you can see that this is an example of an assignment that most likely requires different agents to coordinate to accomplish an overall objective. In this case, one that relies upon web search in order to get the needed information, plus tools and ability to update a PowerPoint deck, which is a completely different set of skills. Specifically, a web agent will access the URL and filter the results to March 1 only and extract the desired information. After that, a PowerPoint agent will receive that information, locate and load the PPT file, write the new information to the correct slide, ensure that all formatting is standardized, and save the changes. Since this is a task that requires multiple specialized skills, a generalized agent will probably be unable to complete the full task from end to end. So, these are examples of where a team of specialized agents would likely outperform even a very powerful generalized model. So, how did it turn out? Here's the current leaderboard for OSWorld. We can see that Claude 3.5 Sonnet is currently on top. Now, Anthropic hasn't disclosed the number of parameters for that model, but for context, GPT-4 has 175 billion parameters, and Palm has 540 billion. So, based on performance and other factors, Claude 3.5 is likely to be around the top end of that range. Most likely, it's a giant model. So, let's move down the leaderboard a bit to Atlas Base 7b. From the name, that would be a 7 billion parameter model, and that one got a score of 14.6. So, how did the team of specialized agents measure up? According to the authors, they achieved a score of 23.85, which would place them in first position, even ahead of the giant Sonnet model. And that was accomplished, according to the paper, using intern VL2 8b as the base model. So that was only 8 billion parameters. That's great performance from a small model. How did they do that exactly? It works like this. For the proof of concept, as described in the paper, those 20 special purpose agents I mentioned are summarized in this table here. You can see that some of them were designed to work with a command line interface, like the Excel example I mentioned. And others were designed to work with a graphical user interface, like the example I gave about filtering a web page to a specific date. Each of those resources was assigned a special class of token that identifies what it can and cannot do. And from that, a meta agent picks the most suitable resource for each task assigned based on the information in those tokens. And this can be done automatically using the chain of thought method, which is a technique used in large language models to improve reasoning abilities by generating a series of intermediate steps, a thought process, when solving multi-step problems. So instead of immediately providing a direct answer, the model breaks down its reasoning into smaller logical requirements and justifications prior to arriving at its decision about which agent to assign to a particular task. Most of the time, a single resource can handle the whole request, in which case the meta agent simply acts as a router to identify where to delegate that. Otherwise, the request is subdivided by the meta agent into smaller tasks, and those are sequenced, and each of those is assigned to the appropriate agent. So to summarize, what the authors have created is a platform and method for aggregating any number of specialized agents, with a meta agent selecting the best resource or combination of resources for each request. And here's a look at the homepage for the project, which includes links to the paper and to the code on GitHub. And as you can see here, it says, "Stay tuned for the open sourcing of our code." All right then, authors, you have our attention. Bring it on. Meanwhile, thanks for watching and see you next time.